not necessarily such an ideal guy, and quite opinionated. You can, I guess, understand if you have such knowledge. But anyway, so he made a mistake here. He also made a mistake of disbelieving entanglement and the whole thing about superposition of states, you know, the famous Schrödinger cat and all that. So very much stuck in classical thinking, although it contributed to the emergence of quantum physics. So this was Einstein. That's the result that Einstein got was wrong, and Peter de Baay from the Netherlands, I think he was at Delft, if I remember correctly, explained it by quantization of these waves I showed you in one of the slides in the beginning. So when you quantize these waves propagating through the solid, you can explain how the solid absorbs heat. And heat, i.e. energy, is used by the solid to create waves with higher and higher frequencies. And that's how you obtain this result. Now, why is this important? I'll explain a bit later, but the importance of this result is such that you can translate it almost verbatim to metabolic activity of living systems, where you have, instead of these waves of tiny atomic and molecular fluctuations, you have enzymes which oscillate. FATPases, if you study biochemistry or cell biology, you know how oxidative phosphorylation occurs in mitochondria. Anybody here knows about oxidative phosphorylation, mitochondrial energy transduction, ATP, and so on? Some people are nodding, some people are not. I don't know what their backgrounds are, by the way. I know Jakob's background. Maybe it's a good point to ask you, what is your background?
I do have a biology background, so I've learned about that a number of times, but not enough for me to.
I don't want you. I'm not testing anything. I just want to know at what level to talk.
I'm in education.
Okay, good.
I'm also in education.
Very good. So yeah, try to educate your future students the best you can.
I will try.
It's an incredibly important job, maybe the most important job.
I'm in science, but I'm specializing in psychology.
Great, we'll count to it.
So, biomedical engineering.
Psychology and biology.
Good.
Neuroscience.
Okay, so we'll save the best for last when we come to the brain and stuff. So anyway, here this model, the Baay model, Nobel Prize winning Nobel Prize winning model of quantum theory of solids, has been translated into the metabolism of living systems, where these oscillators are metabolic, FATPases, metabolic cycles, and then you obtain something that has not been explained until recently for 200 years or so. These allometric scale laws have been known since Lavoisier and Laplace in ancient times. Okay, so we talked about the gifts of quantum physics, but for most people, sort of at the street level, it sounds so arcane, it's so detached from reality. They don't realize that we are really surrounded by quantum-based technology, and this is just a small list of the technology which is enabled by quantum physics, all of consumer electronics, because of the Fermi distributions and conduction electrons. Cell phones, of course, then you have electromagnetic waves, electromagnetic wave transmission, quantization of photons and all of that. Computers, laser scanners, all the spectral line, all kinds of spectroscopy, MRI, NMR. NMR uses spins, I talked to you about spins. Without the knowledge of spin, there is no MRI. We have nothing to explain the images with. And then, of course, precise atomic clocks, cesium, GPS systems, X-rays, solar batteries, photosensors, photodetectors, remember the photoelectric effect, Einstein, PET scans, and all that stuff. So just a small list telling you that pretty much everything you can look around technologically is based on quantum physics in one way or another. So, why isn't it taught in elementary schools yet? Don't know. You probably can answer that question. I think we have, that's again one of my societal comments. I'm hesitant to say it, but I think hard sciences should be emphasized more than they are today, because that's the future. If we want to outsource all of our technological capabilities to China, please go ahead, forget about math and physics. But if we want to maintain our standard of living and keep up with the rest of the world, unfortunately there's no other way, in my opinion. This was not the case, and Kim, if you're not sleeping,
I'm not sleeping.
you may remember the Sputnik and the,
Yeah,
the technological race
that was a
between.
huge impetus to science, yeah.
But also in terms of Western society, which was galvanized to compete with the Soviets.
Yeah.
And so healthy competition in this case unleashed the incredible scientific potential of the US in particular. I mean, the American universities became the best in the world around that time. I think before, I'm no disrespect, Kim, but they were second rate compared to Göttingen, Heidelberg, Oxford, and Cambridge.
Right, yeah.
So that's my appeal to the future educators and teachers to teach your students well. So with this, we'll now look very quickly at these scales, because we are used to thinking about quantum physics as limited to this smallest microscale, but as I showed you in the beginning, everything really is undergirded by quantum phenomena, and sometimes they are coming to the fore, sometimes not. That slide shows you the dimension of the matter, and here you see the sizes of a molecule, micromolecules, nanometer size, atoms, angstroms, the nucleus. So this is the 100-mile. I showed a comparison between the size of the nucleus compared to the size of the atom and separation between humans. If you think of the nucleus as representing a human being, the next human being close to you would be 100 miles away by this comparison, because 99.99% of the mass is the nucleus. And that's the metaphor for the human being sitting in the middle, and then the next one removed by 100 miles. So with lots of empty space in between. And then you see, this is kind of a traditional connection between scales. Quantum chemistry works pretty well, and up to, well, 1,000 atoms is a stretch, but hundreds of atoms perhaps. And then we have hybrid methods, quantum mechanics, molecular mechanics, where you treat most of the protein classically, but the receptor site may be quantum mechanically, and you assign a wave function to the active part of the biomolecule, because beyond that it's very different. We don't have sufficient computational power to represent everything quantum mechanically. And beyond that, we have systems, so macromolecular systems, which have 100,000 atoms and so on. And that's the blurred area, what we would call the beginning of quantum biology. And in particular, things like photosynthetic complexes, microtubules, microtubule constructs such as centrioles. We can start talking about quantum effects at this level, and above. We really have difficulty with the tools currently available. So the cell has about 10 billion atoms. The human body Okay, just to wake you up, how many cells are in the human body? Any guess? Jakob?
No pressure.
I'm not, but, well, it's
Um,
37 trillion, 3.7 10 to the 13th, 37 trillion cells. Okay, somebody has to, we have to believe it, but I think it's reasonable. It may vary, somewhere there, 37 trillion. Trillion is 10 to the 12th. And how many, so another, we'll come to it also in the fourth lecture. How many neurons are, so specific cells, which we hopefully use right now, to a large extent. How many neurons are there in the human body?
Some billion, I think is it?
Yeah, 100 billion.
Yeah.
100 billion. 10 to the 11. Okay, so these are the scale that we should keep in mind, you know, how many. And I told you that quantum mechanics, in the traditional sense, was developed for a single atom or small molecules. We're talking about not only lots and lots of molecules, like its cell would have 10 billion atoms, but we are talking about 37 trillion cells composed of 10 billion atoms, so you do the math. 3.7 10 to the 13th, 10 to the 10th, it's 3.7 10 to the 23rd atoms. I don't even know what word is used for 10 to the 23rd, probably there's no word. Okay, I'll skip this. This is just to give you some masses and comparison sizes and masses. So a cell, eukaryotic. This, I don't know why it's such a small cell, maybe the smallest. So bacterial cells may be, you know, 2 microns and so on. But eukaryotic cells 10, 20 microns or higher numbers. And masses, again, it's easy to remember, 2 to the 10 to the 13th, Daltons. I was at the Masters Defense this week, and it was of physics, and they used a different, yeah, you should know. What else, instead of Daltons, what sort of Daltons are used in biochemistry and cell biology? Grams per mole? Okay.
Grams per mole,
Yeah.
yeah, definitely.
So I asked a trick question, what is a Dalton? It's a gram per mole.
Exactly.
The same.
Yeah.
Okay. Now, it's lingo, just like lawyers have a different lingo, right? Physicists use different names for the same thing as chemists or biologists or as biochemists. Everybody has a different language for convenience and also for defense purposes, right? To sound maybe more sophisticated. So this is the scale of the dimensions of biological systems, and that's a logarithmic scale. Now, if we wanted to represent it as a linear scale, there would be no room, no space on this planet, maybe. So we start from atomic dimensions, or even subatomic. Atomic dimensions are 10 to the minus 10, so that's 1 angstrom. And here you also have, at the bottom, the tools with which we can observe. Remember I showed you how our eyes and our senses are deceiving us because we really don't see much. We do not perceive things outside of the range. The range is narrow. Visual range, acoustic range, and so on. So at the bottom you see the scale with which we can observe things using different technological advances, from microscopy to cryo-EM, electron microscopy, light microscopy, and so on. Now we can go deeper with some things like STM, scanning tunnel microscopy. You can even see electronic charge density. And then electromagnetic scale of wavelengths, which is important because that's what we use as a tool, light and different forms of electromagnetic waves. X-rays, which have the shortest wavelengths and the highest energies. Ultraviolet, UV, infrared, that's longer wavelengths and visible, and then microwave and longer. And yeah. So corresponding to this scale you have, so once again, atom, angstroms, half an angstrom is hydrogen bonds, 3.55 angstroms. Bond lengths typically in chemistry are 2 to 3 angstroms, right? Then we have nanoscale. Nano world is protein, the world of proteins, and macromolecules, nanometer scale. And that's all the rage. Now it's maybe not so hot anymore as a field of science. Nanoscience was nanotechnology. We used to have this institute, which is, I don't know what it's called now, but it was NINT,
National Institute.
National Institute of Nanotechnology. They changed the name to something else, I think, and it's no longer NRC. Okay, and then then we go from nano to micro. Micro, 10 to the minus 6 meters, right? Micrometer. And micro world is the world of the cells. Bacteria are the smallest, and you have, as I mentioned, tens and hundreds of micrometer. Neurons, giant squid axon, meter size, so microscopic dimensions. So cells can be very large, but typically we think about cells as tens of microns. So these different, so the hair I mentioned to you, 0.1 millimeters, it's what, micrometers quickly. How many micrometers is 0.1 millimeter? Sorry, I'm really in a different mood today. Come on.
100?
Huh?
Was
Yes,
100? Yeah.
100 micrometers. And human and so on. So yes, we are very limited in our sense. This is now the time scale. That's even, so how many orders of magnitude we stretch in biological dimensions? Let's say elephant would be 10 meters maybe, or something like that. So 10 to the minus 11 is too small, 10 to the minus 10. So 11, maybe 12 orders of magnitude in sizes. Now, times, actually, it's cut off, and there is faster. 10 to the minus 12 picosecond, picosecond is the typical vibrations of vibrational degrees of freedom in molecules. Picosecond, so 10 to the minus 12, the beginning of it. Then nanoseconds, it's already quite long. Nanosecond time scale is for protein movements, and microsecond would be large conformational changes. And now at the cell level, diffusion, cell signaling, tens of microseconds to milliseconds, and then we have, well, milliseconds are very important in biology. This is the time scale for ion channel transfer of ions across ion channels, milliseconds, 10 to the minus 4. The turnover of ATP, we talked about this, it's a millisecond. About 1,000 ATP molecules per ATPase per second. So a millisecond is the time scale. That means 1,000 hertz in terms of frequency. Frequency is the inverse of time, right? Cycle. So you can go from seconds to frequencies, and so the 10 to the minus 6 seconds, microseconds correspond to the frequency of megahertz, millions of hertz. So it's important to know, because if you want to study with some stimuli, these are typically periodic things, so you have to use frequencies that correspond to these periodicities if you want to cause changes. If you work with ion channels that operate on a millisecond time scale, you don't want to apply signals which are on a minute change of every minute or so. It's just too slow and nothing will happen. Okay. And then we go into longer time. Oh yeah, by the way, another quick question. Human physiology. I would ask some psychologists. What is the reaction time, the human reaction time to any stimulus. The shortest. Of course, you can think about something right now. I don't want you to do that. But let's say if you're trying to quickly answer a question or respond to an oncoming car or train going in your direction, how fast can you respond to that?
Milliseconds to seconds. Either milliseconds or 1 or 2 seconds.
You're in the right ballpark, right?
Specifically, I can't remember.
There were experiments
Yeah.
done by in the 70s by a professor from the University of California, Libet. And he determined. So, any other guesses? Within this range, which is correct.
Half of 1 second.
Yes. 500 milliseconds, exactly. Yes, that's the answer. Which, by the way, if you think about a lot of things that you observe, let's say watch on TV and so on, is hard to explain a lot of phenomena. Feats of athleticism, for example, when basketball players or hockey players or baseball players in particular, how fast they react to the events, it really defies this scale. You can try to explain it by training and intuition and whatever, but I don't think you can explain it by simple, flows of action potentials and triggering your receptors and then responses. It would be way too slow. For these responses are definitely below the 500 millisecond time. So you can calculate it. These days, if you watch, let's say, hockey, as I do, then Bouchard, shoots the puck at the speed of 93 or 5 miles, I think miles an hour. And could be very, I don't know, 10 meters. And so you do the math, how fast it is, and the goalie usually catches it. The same with tennis. Serves at 118 kilometers an hour, more than 120 miles maybe, are not uncommon. And people not only return the serve, but return perfectly. So that's, one thing is to hit it, but another one is to hit it in such a way that you score a point. Okay, so the nice one, human life.
Question?
No, it's okay. Okay, I just had a question about the biological time scales.
Sure.
In case you're moving on. Excuse my physics knowledge is very limited. I'm trying to simplify everything you've said. So in terms of this time scale, quantum physics is kind of looking at how the rate of each of these processes. But I remember last class you mentioned about not being able to predict like a specific atom's trajectory. So in these processes, it's like a lot of atoms kind of working together. So is that explained by like quantum entanglement?
Yeah.
Sure, it's a lot more complicated than that.
No,
but
it's a
trying
very
to
good
simplify
question.
it.
It's really a good question. There's layers to this
sure.
question. The first layer I would say is the uncertainty principle, because if you say delta t, the time of some process, and you want to determine that time, then there's delta E from the Heisenberg uncertainty principle. That means that if you can say that that process took 1 millisecond, then there will be an uncertainty, in other words, error or lack of knowledge in terms of the energy of the process, which corresponds to h bar divided by delta t. In this case, because the Planck constant is very small, 10 to the minus 31st, the error actually is not going to be very big. For small time scales, the errors become significant. So these errors, quantum errors or quantum uncertainties, gradually disappear or diminish. Okay, so that was the first layer.
First question. The second one is that so all of these atoms and cells are acting in the same way.
Yes.
But
So synchronization between atoms is a different kettle of fish, because entanglement allows different atoms, molecules, and other systems to behave as one, because it becomes a multi-component wave function. So just like we will see, for photosynthesis, they measured the distribution of the quantum state over the entire complex, which has 7 molecules. And each molecule has, I don't remember, maybe 20 atoms. So over 100 or 200 atoms, you have a single wave function. And the largest system, to my knowledge, for which a wave function has been determined, quantum mechanical wave function, is a protein which is about, not a huge one, but I think it's 10 kilodaltons, so 10,000 atomic weights, hydrogen masses. It doesn't mean that bigger than that is not coherent or quantized. It just means that we have not been able to measure it yet. So I hope it explains it.
It does, yeah. And then within entanglement, usually, what is the furthest distance they've been able? Because I'm sure you can't.
Infinity. Molecules.
How do they measure it to infinity?
Ah.
Like experimentally, how far have they been able to prove entanglement?
Maybe miles.
Okay.
Yes, but in principle, these. So this is a bit tricky because it's easy to theorize and hypothesize.
Right.
It's difficult to measure
To
things
prove it.
to prove it. So theoretical infinity, but practically, the problem is that you have to isolate them from the environment, and isolation is a problem because interactions disturb or decohere systems, and therefore you don't know, it destroys this entanglement. That's one of those scientific debates raging in the community because people say that for biological systems to be quantized or in a quantum state, they would have to be shielded from the environment, and the state has to be protected in order not to be disturbed by thermal fluctuations, and we'll talk about this a little bit today. So, perfect question, thank you. And then let's talk, so time, in biology, time, space, and energy are important to keep in mind. So we talked about time and space. Now let's talk about energy. These are the characteristic energy scales for the foundation of biological systems. All the bond energies and the distances range from so again, a different scale of energies from 1 kilocalorie per mole, maybe hydrogen bonds, or half a kilocalorie per mole to about 100. And these are the elementary molecular bonds, but of course then we mentioned ATP, and that's what somebody, Mike Persinger, the late Mike Persinger, I don't know if anybody knows, Kim, you probably know now. He was professor at the University of Manitoba, I believe, and he coined this term, the quantum of biological energy, or biological energy quantum. And that's the amount of energy generated in ATP hydrolysis. GTP is a bit smaller, but ATP hydrolysis produces about 60 kilocalories per mole. So these energies above are chemical energies, and that is biological energy. So quantization in biology already starts with energy production and energy consumption. Production is from glucose, fructose, and so on. Breakdown of nutrients and the fundamental molecules like glucose and fructose, and they put to biochemistry again. Another question I'll answer myself, but maybe you remember how many ATP molecules do you obtain from one molecule of glucose? That's the from glycolysis. Yeah. Glycolysis. Sorry.
32?
32, yes.
Yeah.
Yes, from oxidative phosphorylation 32, glycolysis 204 amino acids. So it's about 10 times less efficient overall. So glycolytic switch, it's a very common also, but also pathological change in cells when they require energy quickly. So when you do a sprint, you use glycolytic energies mode of production, glycolysis rather than oxidative phosphorylation, which is much longer and but more efficient, 10 times or so. But anyway, so that's the biological energy, and that's something to think about. There is quanta. You don't have half of ATP, and not only that it's produced like that, but it's utilized like that. Almost every biological movement or deliberate act requires 1 or 2 or 3, sometimes 4 ATP molecules. Kinesins moving on microtubules, dynein, myosins are sliding on actin filaments, FATPases. All of this uses integers of ATP, so it's quantized by energy. It's not as small an energy as could be in quantum systems, but it is. It is quantized, no two ways about it. And even if you think about light, photosynthesis, light comes as in quanta. It could be a lot of these quanta. And by the way, maybe I keep thinking that one day I would like to calculate, it's a quick calculation, how many light quanta are received by plant's leaf in 1 second. That's something to calculate. But these are quantized things, both in, so metabolism, either plant or animal metabolism, are necessary conditions to sustain life. Without metabolism, there is no life. Life ends very quickly. Critical thing. And both plant and animal metabolisms utilize quantized energy. And there's more to it. So, not just because we count them as 1, 2 integers, but also because these processes involve quantum tunneling and quantum wave function superposition. So, important. Not, if you go to, again, YouTube, the best source of, I'm kidding, information, to lectures on quantum biology, you will not hear about this. Maybe never. Only my lectures talk about metabolism being fundamental to quantum biology. Okay, and one more comment about this slide, and then we'll accelerate a bit. So, biological energy quantum, about 60 kilocalories per mole. There's some other units, but let's stick with these. And then, on the other hand, there is thermal noise. Biological systems, by and large, us included, live at warm temperatures, 36.6 Celsius. So that temperature creates non-stop fluctuations. So things jiggle around. And anything that is at this level of energy or below is basically noise. And that value is 0.6 kilocalories per mole. So you see, there's a big difference between deterministic, not deterministic, it's a wrong word, but deliberate motion that in biology that requires energy quantization, ATP, or sometimes GTP, and omnipresent thermal fluctuations, thermal noise. But the gap is 100-fold, so 0.6 to 60, that's 100 times. Therefore, thermal fluctuations do not interfere with quantized energy that causes movement in a deliberate way. Okay, I just wanted to compare these two, that's important. See, KT at 310 Kelvin is 0.6 Kelvin, and then you have biological energy quantum 60, so a factor of 100. I mentioned to you this hierarchical organization of matter and the difficulty of connecting between hierarchies. And each hierarchy, by the way, over the course of scientific development has been classified and codified as separate fields. That's why we don't communicate so well, because we have degrees of separation, many degrees of separation. Let's say quantum physics would be at the bottom, typically, elementary particle physics, quantum field theory, quarks, and so on. And from all of this elementary particle physics, if you go to condensed matter physics, for example, the next level of organization, and you talk to somebody who works in this field, they only need electrons and protons, that's it. everything else doesn't matter. And then you go from, let's say, atomic physics or molecular physics or molecular physics to chemistry. They will actually only talk about ions and molecules, right? Well, valence, right? So again, most of physics for chemistry is redundant in a way, or maybe not so. But they think in different terms. I've attended many PhD defenses in chemistry, and I was amazed how three-dimensional chemists think. You know, stereochemistry. They know where the bonds are, you know what geometries are, and how this can connect with that. I cannot do that for the life of me. And then from chemistry you go to biochemistry, and all of biochemistry needs from chemistry more or less is nucleic acids, amino acids, and sugars, and a few groups of molecules, and maybe some ions for catalytic purposes. So, and why is that? And not just the information reduction necessary to be able to do some useful work in a given field. You know, if you were to worry about quarks in biochemistry, you would never solve any biochemical problem. But also in terms of elements, you have different elements, different sets of elements to work with. Like protein biochemistry, you deal with amino acids and peptide chains and protein. That's it, more or less. But also rules change. So within each group, each hierarchical manifold, scientific manifold, you have elements and rules, shortcuts. You cannot go back to solving relativistic Dirac equations for biochemical molecules. You'd spend the rest of your life just solving one equation for all of these complex molecules. So the rules change. You use shortcuts. You kind of don't look down anymore. And biology is not even shown here. Okay, so, and that also speaks to the different levels of modeling. And this shows you now connecting the scales, the time scale and the length scale, and so picoseconds, nanoseconds, microseconds, milliseconds, seconds, time on the horizontal axis, and then you have vertical axis with nanometers, micrometers, millimeters. And in each box you have different levels of simulation, modeling, or representation of the world within which you operate. So you have quantum mechanical models in this nanometer, picoseconds, maybe now longer, up to nanoseconds. Then you have atomistic models, which are molecular dynamics typically. Then you have coarse-grained models where instead of looking at each heavy atom or even all atoms, you look at groups. Let's say amino acid becomes 1 point. The entire amino acid is 1 point. Just like I showed you in the beginning, how you have to delve deeper to see all the granularity of the world. And then you go from, let's say, milliseconds to and micrometers above with continuum models. And that's your metaphor of the table, solid table. Now it's all continuum. You don't see any granularity in space or time. So you have to realize that at each scale we're making drastic approximations to how we see the world. So the question is, what we don't see? And that's one thing I learned from this amazing book by Al Scott, The Stairway to the Mind. I highly recommend. The book was published maybe 20 years ago or more, but it's really very insightful. Is that there exist real barriers to knowledge, not just the Heisenberg uncertainty principle, but computational barriers. So if you have to deal with a system that may have 10 to the power 110 states, you will never be able to even inspect it, let alone do any meaningful processing of the system. Why is that? Well, the argument is very simple. Imagine that the entire world is one big supercomputer. And imagine that supercomputer operates on the atomic scale, which is a picosecond, transition of the atomic states. And also imagine that each bit in that system is represented by an atom. Every atom in the universe performing computations on a picosecond time scale. And if that universe was a big computer, we are living in the matrix, right? So the universe is a big computer. Did calculations from the Big Bang until now, which is about 14.5 billion years. And so if you calculate this in picoseconds, and the number of atoms, which I think is 10 to the 80th, and the number of picoseconds is 10 to the 30th, something like this, you make the product is 10 to the 110. Which means that, so it's 10 with 110 zeros. It's a very big number. Nonetheless, it's a real computational barrier to any system or set of objects which is that big. And you might say, okay, this is fanciful because there are no such objects, there is nothing that is that big. No, you'd be completely wrong, because even the number of amino acid sequences for proteins which are 500 amino acids long is way bigger than this. The number of DNA has a billion base pairs. And so it's 4 to the power of 1 billion. This is way bigger than this. In other words, if you want to do brute force prediction of protein structures from the amino acids, I want to design a protein find the best one from all the possible proteins of length 500. You will never even scratch the surface of it to answer this question. You can only use some kind of approximation or some similarity, or maybe artificial intelligence, which is based on prior examples, right? But where do you find 10 to the power 110 examples to use as priors? We don't even know how many classes of protein may exist in principle. Okay, do you get this? I hope this tells you. Some time ago I worried about whether we'll run out of musical tunes. You can imagine there's 12 notes, right? Even in one octave. And if you have a sequence of 100 notes, so 12 to the power 100 would be 100 note piece of music spans an immense set, in principle. So music is inexhaustible, which when I discovered myself, I was very happy about. Although I'm not a composer, but I love music. And of course you can extend it to work of art, to poetry, to literature, and so on. There's a huge number of sets which are immense and therefore inexhaustible. I think this is enough for maybe some of you to think about today. That we live in a world of inexhaustible possibilities. And that's also kind of quantum. Okay, so what is life? So Aaron Schrödinger wrote, actually this was 1944, I don't know why, 1935 I think he got a Nobel Prize. So the book was written in 1944, he was in Dublin, at Trinity College was Dublin at that time. Although he was not Jewish, his wife was, and so they escaped the Nazis in Austria and Germany. And he spent that time thinking, and he wrote that book, which is still very powerful today. Although there were no crystals known, no protein structures known at the time, but he came up with these various fanciful ideas about quantum coherence in biology and aperiodic crystals being proteins and paradoxes of entropy reduction and so on. So that kind of unleashed the interest of physicists into biology, and 1944 is the correct date. And so somehow we need to what's the word for it? Reconcile Schrödinger with Darwin. And on the one hand, you have something incredibly precise and very mathematical, Schrödinger's equation for small entities, and on the other hand, you have natural selection and competition for biology, as Darwin showed us. And I think this is not a contradiction. What I'm trying to say here is that there was period of 2 billion years on this planet of natural selection competition and selection of the best suited organisms, species, for a particular set of conditions, which meant optimization of living systems to, let's say, living in extreme temperatures. There are some extremophiles, various species that survive in extremely cold, extremely hot, extremely acidic, extremely dry, moist, and so on, all kinds of conditions. And therefore, if my argument is that quantum processes are not that hard to optimize, we keep on optimizing them for larger and larger systems and for more and more complex systems. As I mentioned to you, even the smallest protein has been shown to have a quantum state. So I don't think it's a big stretch to imagine that all of life forms utilize quantum processes in some form, and the most advanced, probably. I'm guessing I'm making a statement that could be challenged, but the most advanced biological system is our brain, right? So we'll come to it in the last lecture because I proposed, and other people, it's not my idea solely, but that the human brain utilizes quantum information processing at some level, and otherwise it's impossible to explain many things. So this is the topic of quantum mechanics in life. So entangled states, and the objections abound to this statement. So you can find a lot of objections to quantum biology because of the size, big living cells, which, as I showed you, it's not that big compared to other quantum systems. Even microscopic quantum systems exist. Life is too hot. That means compared to things like 3 Kelvin for superfluids or 115 Kelvin superconductors, but it's not, because there exist also quantum states at room temperatures, and I showed you crystal lattices, ferromagnets, and so on. So that's not, and most important, I would say, is quantum mechanics, quantum field theory have been developed for equilibrium situations. That is, systems which are left alone and allowed to equilibrate and find the lowest energy state. Living systems are not at the lowest energy state, quite the opposite. Metabolism raises the energy to the level suitable for particular demands of the living function. Therefore, we call them far from equilibrium. And that may, if you think in terms of equilibrium system, they will very rapidly drop down to decoherence of the quantum state. But if you resupply it with energy, you can maintain that system, just like lasers. You have to keep on pumping the laser with energy to maintain the excited state, population of the excited state by molecules in the laser. Just the same way, I believe living systems utilize metabolisms to maintain this far from equilibrium quantum state, which otherwise would be, and is, at the point of death, equilibrating to classical equilibrium. And then the complexity, the complexity of biological systems is just in the eye of the beholder, because life, again, had 2 billions of years of evolution to start from simple, very simple constructs to more and more complicated, including mitochondria, which were incorporated into simple cells and became part of the cell to provide continuous energy production. And then multicellular organisms arose, and then you have the entire evolutionary ladder. So the complexity of biological systems is simply because physicists, quantum physicists in particular, are not used to heterogeneous structures. They work on repeating lattices or electrons hitting protons or being hit by photons, and so on. So I think that's a completely bogus argument, the complexity. It's, in fact, probably the opposite. Complexity allows you to find the most suitable conditions, and optimization may occur. And then the other arguments about reality, what is reality? Life is real as opposed to quantum. No, I showed you, when you zoom in, it really becomes all fuzzy. So these are the objections, but there is still a lot of features of life which cannot be solved by molecular biology, structural biology, genetics, biochemistry, cell biology, you name it. None of these sciences address even such things. For example, collective dynamics of many degrees of freedom. All of these sciences look at individual cells or individual proteins or protein complexes, 3, 4, maybe, if you're lucky, maybe 10, but not the entire system as working as a whole. There is a glimmer of hope. 20 years ago, a new field of biology was created in Seattle, Washington, namely systems biology, by Leroy Coode, who was given, I think, a big grant from NIH, if I remember correctly, to set up an institute. Systems biology looks not as at the biological system as individual elements coming together and in the binary reactions, but as systems of systems, where the dynamics, collective dynamics of the entire system is investigated. It's still within the classical paradigm, but systems biology is a step in the right direction, in my opinion, because it moves away from this, focus. And by the way, no disrespect, I think it's important to know all of the elements, all the proteins, all the enzymes, and all that stuff is very important to know. But then, once we have all the Lego pieces, how do they organize it? Self-organize, in fact. Right? And there is no example in science to start a new life from scratch. So this is one single continuous experiment that has been going on for 2 billion years in all life forms in parallel. So each living system is its own laboratory of solving problems. All right, so yes, hierarchy, dynamical order, long-range correlations. That is how organization allows for correlated activities of distant parts of the system. Okay? How does that happen? And you can imagine how many lines of communication would have to be for each cell to talk to the other cells. There's 3.7, 10 to the 13 cells, and each cell would have to communicate with another. So it's roughly 10 times 10 to the 26, 10 to the 27 binary interaction in the cells if they were all supposed to communicate. 10 to the 27 interactions take place non-stop. That's not possible. There must be something else. It's not binary, it has to be collective. And this, so metabolic, for example, metabolic synchronization is one possibility of synchronizing operations, working on the same time scale. So that allows you to avoid interference and noise. Okay, so these are the kind of unanswered questions in biology, maybe sometimes don't even ask. So this is a Wikipedia definition of quantum biology, application of quantum mechanics to biological objects and problems. And it says, typically non-trivial. What does it mean, non-trivial? It means, yeah, we know that chemistry is quantum physics, really. So, and biochemistry is chemistry, therefore biochemistry is quantum physics, and cell biology is really biochemistry, so cell biology is quantum physics. Not this way. Non-trivial means that there is something exotic happening. So like this entanglement, wave function collapse, tunneling, superposition of states, and so on. And I think There are many examples, not many, but several examples of this non-trivial behavior. One of which I mentioned to you already is photosynthesis, and then metabolism, tunneling in the metabolic enzymes of the mitochondrial wall, inner mitochondrial wall, and non-locality, entanglement tunneling. So there are examples of this. These are the exotic things that quantum biology is looking for, but I think we may be also barking up the wrong tree. That is, that's not all that quantum means. I already mentioned to you energy quantization. I already mentioned to you metabolic statistical level of quantum physics, which is incredibly important. So, and there are some other examples scattered so far, but and nobody has really gathered that together in a consistent field. Quantum biology actually has been talked about since almost the beginning of quantum physics, and quantum physicists of note, such as Niels Bohr, Werner Heisenberg, Erwin Schrödinger, who wrote this book, John von Neumann, Carl von Weizsäcker, Lasse Weizkopf, Eugen Wigner, Freeman Dyson. There are a lot of very interesting YouTube videos with Freeman Dyson talking about science. He passed away a few years ago, one of the greatest thinkers of all time. They all thought and speculated that quantum mechanics is essential for understanding life. In other words, life, in terms of random collisions of molecules, cannot really be explained. It has to be something else. And that's why quantum mechanics comes into play by allowing these entanglements, correlations, collective modes, and synchronization to occur. But not, I'll just finish with this metaphor. I often wonder, if you think about a big city like Beijing or New York or London, how the hell does it work? There's so many people and so many different articles. They need this, they need that, and everything is available. There are restaurants, there are cinemas, there is transportation and sanitation. Everything is on time. How? If you were to design from scratch, you would never be able to do it. So that's the same thing with life. If you look at the living cell, it's so busy, it's so many things happening, so many different proteins, and they all come together. And I kind of answer my own question by the following thing. New York or London started as small villages, and it's organic growth, just by trial and error. We need more milk. Okay, so therefore we send orders for milk. If there's no milk, okay, people will not live here. So it's a feedback loops that are created for demand, supply and demand. And then you organically grow the city. It's not that there's some master planner there. Well, there's some, even in Edmonton, there are city planners, but I think they're terrible. In fact, they do more harm than good. Organic growth of a society is the best because it really responds to the demands in real time. Right? You have supply chain issues, and somebody can make money by stepping in and making it more efficient. This is how it works, not by somebody who has a salaried job like us, who will design supply chain. No. So the same way biology, I think, and with this 2 billion year evolutionary process where the best adaptations survive, you can solve these problems. So here's a list of, and I'm finishing today's lecture in a minute. So I mentioned quantum metabolism, photons, biophotons. That's a huge field that talks about and investigates emission of light by living systems. All living systems emit electromagnetic waves as a result of their byproduct of their metabolic activities, and some people correlated with different phases of cell cycle. For example, cell division has a different profile in terms of biophoton emission, and photons are quanta of electromagnetic radiation, so that's a reflection of that. Then you have photosynthesis, there's solitons, Davidoff solitons. In other words, propagation of energy signals through structures such as alpha helices in DNA or proteins signaling inside cells cannot be done by random diffusion and random collision. It has to be done by specific channels of communication. And these channels must be fast enough to respond in real time. So, famous Ukrainian physicist, by the way, Ukrainian, Jewish, but Ukrainian, Alexander Davidov came up with this idea of quantum electronic excitations coupled to phonon modes in alpha helices of proteins could be very useful in sending signals. Actually, electromechanical transduction, triggering changes in the cell. I will come to it maybe next time. And then there is long-range coherent excitations by Herbert Froelich, another physicist who just missed narrowly a Nobel Prize for superconductivity, which he actually should have received, but that's another story. He, in his last days of his life, years I would say, came up with this idea that membranes of living systems of cells have dipolar head groups, and these dipoles can oscillate at terahertz frequencies, and by doing so they can have electromagnetic signatures and communicate with other cells, which actually has been demonstrated later on by various scientists that cells communicate electromagnetically, not just by mechanical or chemical signals, molecules, but also electromagnetically. They sense other cells. And then finally, you know, I will just leave you with this, that this cellular water is an incredibly interesting system, which is unfortunately very poorly investigated. There is a scientist, colleague of mine, Jerry Pollack at the University of Washington, Seattle, who has spent the last 25 years of his life investigating, showing how biological water is organized in a kind of new phase. He calls it the fourth phase of water, which is between ice and water. So like a liquid crystal. And that facilitates interaction between proteins and recognition between proteins and enzymes and so on. So that's another YouTube video. You look up Gerald Pollack, a visionary scientist, but he's not alone. There are some other people. Somebody wants to get in, I'll get out. So thank you very much for this. And
Great.